Thanks a lot for inviting me. This is the first conference I've been to for 3 years, so it's really great to see old friends and new friends. I'll have to turn this on. Now the advanced slide works. Here we go. Okay, so what I wanted to talk today was a multiphase flow where you have sediment-laden rivers going into the ocean. And so there's lots of interesting dynamics that could be occurring here. You could have a landslide and material going all the way to the bottom as a very dense current. It could fall down, lose its sediment and then rise up again. Or you could have what I'll talk about mainly today, the case where you have a river plume with sediment in it which becomes unstable and plunges down. So this nature of having two phases, having the salt and water contrast and the sediment dynamics, leads to all sorts of interesting behavior. So all the experiments that I'll show today, I didn't do. A team of talented students did. Right now, Emile Tevian is visiting from the Netherlands, but in the past, George Liu was doing some of the work. He's now at Columbia, and Shahrazad did this as part of her PhD thesis. So the sort of interesting behaviors that can occur, this picture here shows the case where you've got a fresh layer of water, like the top of the ocean, salty layer at the bottom, and then I'm releasing an intrusion of sediment-laden fluid. And there's quite complicated behaviors that can occur. The simplest case is it's got an intermediate density and it forms a gravity current that spreads quickly through the tank like an intrusion. If the settling velocity is very low, nothing much really happens. You can also have a case where the gravity current spreads through and sediment falls out the bottom. And if you've got a mixture of alcohol, sediment and water, you can get this third case where the sediment goes up to the top. So this was the paper George Liu and I published last year qualitatively described these different regimes. But if we want to try and extrapolate properly to the field, we need a theory. So today I'm going to try and talk about a theory for how fast this sediment at the bottom falls down and how much faster it is than the Stokes settling velocity. So I'm glad that Eckhart and Tom and others are in the audience, because I'm talking a little bit about various theories they've got and when they might be valid and when they might not be valid. So I used to mainly do lab experiments. Now since moving to Canada, I've got quite interested in field work. And so the particular field situation that I'm interested in is in Vancouver, which many of you might have been to. And so the big river that flows into Vancouver is the Fraser River. You can see the airport just north of Richmond. When you're coming into Vancouver on the aeroplane, it's really quite striking, this big plume of sediment-laden material that flows out into the Straits of Georgia. It spreads out at least 20 kilometers offshore. And the Fraser River is a massive river. At peak flow, it's about 15,000 cubic meters per second. So this is, it's one of the big, great rivers in North America. And so in May and June, when the snow's melting in the mountains, you get a lot of flow in the river, a lot of erosion of material, and there's a very high sediment load. So you look at a picture like this, and you can see the sediment at the top. What we don't know is where does the sediment go beneath that plume. So that's the kind of question I'm trying to get to, where I want to use my lab experiments to come up with a theory that we could test in the field. So for the last 25 years, various people, including some in this room, have been thinking about this problem. Kyle's going to talk about flocculation later today. I don't know anything about flocculation. Flocculation is probably really important too. There's another instability I'm going to talk about now, which is, this is a picture from our paper, but there's similar pictures in papers by Maxworthy, Eckhart's group and others. So the idea is, on this first graph here, the y-axis is depth, the x-axis is density, and I've got a picture where we initially have a small amount of sediment at the top, and so it's lighter than the fluid layer below it. So we've got salt water at the bottom, a mixture of fresh water and sediment at the top, but it's got sediment in it. So the sediment has a settling velocity, and at the bottom of that interface, some sediment moves from the freshwater layer into the saltwater layer. And so after a certain time, delta t, you now have this nose region, which now is a mixture of sediment and salt, and so now it's unstable. And so this is a thin boundary layer, which is probably balanced by viscosity, so it grows and then becomes unstable, and then we get these plumes of sediment-laden fluid going down beneath that layer. So I'm certainly not the first person to see this. This paper's going back to the 80s and 90s where people have seen this before. The big question is, what is this velocity? Everyone agrees it's generally a lot faster than the Stokes settling velocity, but I would like to come up with some scaling for what's the controlling parameters and how fast does it actually go. And this might allow us to extrapolate from the lab to the field situation. So looking at this picture, the key things you might think are important are the settling velocity and then also the density contrast between the top red layer and the cold, dense blue layer. So with that in mind, one parameter that might be important is the density ratio. What's the salt contrast compared, the stabilizing salt contrast compared to the destabilizing sediment contrast? And so quite a lot of previous papers have been in terms of this density ratio. You could also think another parameter might be just, we don't care at all about the salt, we only care about how much sediment is in the top layer. What's the sediment contrast? And so you could write that in terms of a reduced gravity. So some of the next few slides I'll be talking about this density ratio, but later on I'll just be talking about this reduced gravity for the how much sediment there is in the top layer. So I've got a series of videos that Shahrazad made for a PhD thesis, and they qualitatively show the sort of behavior we're trying to explain. And for her thesis, she was doing everything in terms of this density ratio. So there's a series of 5 videos. The first one, there's no sediment, and so that's essentially a density ratio of infinity, a regular gravity current. And then we add more and more sediment to the flows, and you see the behavior. And for the very last one, we had so much sediment that it's actually denser than the salt water and just plunges straight to the bottom and forms a turbidity current. So these videos are kind of nice, but they're qualitative, but you get to see the general behavior. So on the left, we have a barrier which we mix the fluid behind. We pull the barrier out, and then the fluid is able to flow through the tank. So this very first case, there's no salt in it, just a freshwater layer, forms a gravity current that spreads through the tank. This is like a river going to the ocean. And this has been, there's hundreds of papers that describe what this looks like. This is really well understood. Now the next slide, we add some sediment to it. So it's still fresh, so it's still lighter than the surroundings, still flows as a gravity current. There's not much sediment load, so you have to wait a while. So it goes all the way across the tank. This is a 6-foot long tank, by the way. It's about as big as what you're seeing on the screen. The videos are sped up, but now if we wait a little while, you think nothing's happening, this is really boring, why am I watching this video? Just keep waiting a little bit, and what we'll start to see is these very weak little fingers that start to form as sediment. And so they grow and they fall out from the tank. So what I'm using here is I'm using a silicon carbide grinding powder. It's very small, about 8 microns. The settling velocity will be very slow, and so what's interesting here is that these plumes are now settling down quite rapidly. They're transporting material from the top of the water column to the bottom of the water column, order of magnitude faster than the Stokes settling velocity. And you can start to see there's some organized, coherent structures happening here, but it's still pretty slow. Now if we add more sediment, so here it's only slightly stable. It's only, the bottom layer is only 1.4 times denser than the top layer. So the density difference is weaker. It's transporting horizontally slower, but you see very quickly we form these strong downward moving plumes, and they're quite a lot faster. So, you know, they're falling very rapidly compared, so it's exactly the same particle sediment settling rate, but they're falling a lot faster. And then I move to one where it's marginally stable. It's only very, very slightly lighter than the bottom layer. And you can see it hardly spreads out at all. It's barely goes into the tank before you form this turbidity current. It's going to form a turbidity current at the bottom. So we're converting something that was slightly lighter, sinks down, forms a turbidity current at the bottom. And so this is the process geologists are quite interested. How does a river that initially has all the sediment at the top transform to something that flows on the bottom of the flow? And so I first heard about this process 10 years ago here, when talking to Eckhart and also talking to Savitsky. It's a process geologists are quite interested in. And then we could have the case where it starts off denser than the surroundings, plunges immediately to the bottom, and this is your classic turbidity current that many of you are interested in. And there's analogies to pyroclastic flows that look a bit like this. So this is the work Scheherazade did. It was really nice, beautiful visualizations, but it didn't quantify anything. So how do you go about quantifying some of these flows? My colleagues, Phil Hill and Gwen Linton in Victoria, British Columbia, made this nice little video, just how you go about the process of digitizing one of these pictures. So they took a video Scheherazade made, and you just start stacking up all the slices at a particular time to make what's called a time slice video. So it kind of goes a bit slowly, but you end up with a picture on the top where now we've got depth as the y-axis and time along the x-axis, and you can it's a time slice of how the sediment moves down. And so this is a simple way to digitize images and work out speeds in them. So if I just work out the slope of that, I can work out the velocity. So I can take all these videos, I can process them, and I can come up with a representative velocity. I tried using POV to do this. It doesn't work very well because of the attenuation. I've got an ADV, which also doesn't work particularly well. So this fairly simple method is the best way we found to do this. And this is a pretty standard method in lab experiments to turn pictures into velocities. Okay, so this is the sort of image we can make from a lab experiment. You can also make the same sort of picture from field situations. Eckhart?
Just wondering, the green and the red line, what are those? You need to use them. Oh, sorry.
Oh, they're just showing at that particular, so there's a red line, and then to the right of the red line is a profile showing what the magnitude of the pixel intensity is.
Oh, I see, okay.
So they're just, yeah, so it doesn't have a scale on it, but it's a kind of a relative scale that shows more. So at the very bottom, the tank's black, so it's just showing what's in the photo. So it's sort of related to the sediment concentration, but because the photos aren't very clean, you get these funny shapes. So you can sort of see the bottom of the tank in this image here. It's sort of blue along the bottom and then turns yellow. Does that make sense, Eckhart?
Maybe.
So it's just at two locations. So
Is it two locations of density, or is it?
Yeah, two locations. Oh. So one's at 591 pixels, the other one's at 1086 pixels. Different locations in the tank. Do the same thing, you get slightly different pictures. So where you make the measurement obviously affects the velocity. So the reason Phil and Gwen were doing this was so you could do the same stuff with field data. So they have been, they're geologists at it's a federal institute in Patricia Bay in British Columbia. Institute of Ocean Sciences, that's right. It's a premier institute of Canadian oceanography. They've been monitoring the delta of the Fraser River for quite a long time and have been quite interested in what are the physical processes that determine how sediment deposits in the Straits of Georgia. There's some practical reasons you want to know this for dredging the river and flow stability, but there's some scientific interest as well. So what they did, they deployed a bunch of instruments about here. They were monitoring various techniques. And so the river, during the course of the year, the discharge is the orange line. In May and June, it really peaks. There's all the snow melts, so the flow goes up an order of magnitude to 10 to 14 cubic meters a second. The sediment concentration also peaks then too. Most of the time it's got some sediment, but it's not particularly high, but in May and June, it peaks up at about 1.4 grams per litre, which is quite a lot for a river. It's a big river flowing really quickly. The seawater freshwater difference is about 30, so the density ratio you'd expect is about 32. So this is a number that you might be able to compare with the lab experiments, but it's not quite obvious how to do that. So what they were deploying off the mouth of the Fraser River was an instrument called an acoustic Doppler current profiler. So these are the sort of workhorses of a lot of limnological or oceanographic work. They're primarily designed to measure shifts in the Doppler backscatter, so you get the velocity through the water column. A secondary thing that they measure is the intensity of the backscatter in decibels. So This is related to particle concentration. So higher backscatter means more particles, lower backscatter means less particles. So you can relate this to particle concentration, but you need to ground truth it. So what happens in the river? It's a little bit complicated. There's tides going up and down. So the point where the salt water comes up the river, at high tide it's higher, at low tide it's lower. So at high tide, the salt intrusions goes further up the Fraser River. At low tide, it gets pushed back offshore. This is supposed to represent where their ADCP is. So at different times of the tide, you might be seeing the river plume or not. So when you change from a high tide to a low tide, the ebb tide, no, the flood tide, when the tide's falling, you get this big pulse of sediment going off the river, and it's a little bit like the dam break experiment. There's a sort of a time scale we start and where it flows out. So what they're particularly interested in is when the tide's falling, the flow gets really strong and comes out during the times of the year where there's also the really high sediment load. So when they do that, they want to know what's the rate at which the particles are falling out and settling down there. So they had this great paper. It came out last year. Probably haven't read it. But the main result was if you make these same sort of time slice images, so you have depth on the y-axis, and so one time they deployed it in 100 meters of water. They initially deployed it in 40 meters of water, and this is time in hours on this axis. So this is showing over the course of one day as you go through a high tide, a low tide, and a high tide again. And this is the bit they're interested in. There's something coming down through the water column. They know it's from the backscatter. It's probably sediment. And by working out the slope of that, you can figure out how fast is that falling.
CP is actually located in one location and it only measures properties at that location, or does it look up the slope and can it measure?
So they're really good instruments, but you put them in one location, but you can leave them there for months. So you get a time series at one location for a long time. And so this process, they only see it during May and June when the river flows really high. Early in the year when there's less sediment load, you don't see this. So this gives the hint that the reduced gravity is important parameter. And so this is the sort of graph they're most interested in. The top axis is showing the tide, so the water level is changing by about 3 meters over the course of the day from high tide to low tide. So just as you get to low tide, you get this the plume moves out over the sampling site and you see this big drop, which I've indicated with the yellow arrow going down. They're also directly measuring the velocity, the vertical velocity from the ADCP. And the important point is that you're seeing something falling down at about 1 to 2 centimeters a second. Now, I want Kyle to tell me later on today this could or could not be from flocculation. But what we'd like to do is, can we predict 1 to 2 centimeters per second from the lab experiments we're doing? Is there a way to look at the lab conditions and then look at the field conditions and say, this shows this process is relevant? So earlier this year, my colleague John Hughes Clark's got this fancy ocean mapping boat, which he's got tricked out by the Office of Naval Research. It's got side sand sconers, it's got optical, acoustic, ADCPs. It's really fancy. So he's been quite interested in sailing up and down near Steveston at the mouth of the Fraser River, and I've joined him to try and sample what's going on. So next year we're going to have a big effort to do this in May or June during the freshet. So what did we find when we went out this May? It's quite dynamic. As different phases of the tide, what you see is this intrusion moves up and down the river many kilometers. So the bottom panel is velocities, so upstream and downstream. The middle panel is the sediment concentration measured by optical backscatter. So we lower a probe through the water column. And the top panel is the salinity. So there's a lot of stuff going on here. There's really strong shear, time dependence, curvature of the river. It's a really complicated situation. And I've got to say, it's a bit intimidating after you've been doing lab experiments, to just try and deal with all this. But this is the goal. Can we understand this? Can we look at these maps of sediment concentration and say yes or no, we would have measurements? So as you were asking, the ADCP measures at one point over time. Here we go at one time. and get some spatial measurements. So we're hoping to try and compare the two to get a really good answer. So we need a theory now. What was the theory about what's doing it? So the key thing is to start off with this Stokes settling velocity. And here's a little video I made for my class where we have different silicon carbide grains. This is the one we're using in the experiments. It settles out really slowly. So big particles settle out quite quickly, and then there's a gradient. And if there's nothing else going on, the Stokes settling velocity is the sort of default assumption to what's happening, assuming there's no flocculation. Okay, but we want to know what this instability is. What's determining this speed here? This is what we can measure with the ADCPs in the field. It's what we measure in the lab. So can we come up with a theory that we can describe that with so we can extrapolate well to the field situation? So Eckhart was one of the ones who got me first excited by this. And so the theory of Eckhart's, he has some numerical experiments that were published in Journal of Fluid Mechanics. I think they're in the limit where particle settling is assumed to be relatively small. And the scaling that Eckhart predicts, based on that assumption, is that it scales with the viscosity. It's about the instability of the boundary layer. So viscosity is important, and the reduced gravity is important, and it goes to the 1/3 power. So that's something we can test. We can change the reduced gravity in the lab, and we can see, does the thing we measure actually scale with this? So it's possible Eckhart's in a different limit than what I'm exploring in the lab, but this is one prediction. A second prediction, another numerical experiment was from the group of Tom, who's sitting in the audience somewhere, I hope. His numerical experiments look similar to Eckhart's, but there's some important subtle difference between them. I think he's looking at not at the limit where particles are really slow. So the pictures you see look similar. This picture here is supposed to be a 5 centimeter by 5 centimeter real scale. And here we've got the concentration in grams per liter. So this is proportional to the reduced gravity. Here's the velocity. But you see it clearly depends upon the particle size. So now small particles of 4 micron, like I use in the lab, have slower convective velocities than the 20 micron particles. But this slope here is sort of consistent with this G prime to the 1/3 power law. So there's a bit of difference that I hope later today to understand between these two numerical experiments. Both really bright guys. There's obviously a different assumption made somewhere in the simulation. Now the paper most people actually quote on this topic was by a fellow Australian called David Hoyle. This is part of his PhD thesis at University of Buffalo. And so the tank we're doing our experiments in is actually basically the same as David's tank. And here's some pictures from his paper from '99. I haven't spoken to David about this, but this is the theory he has. I find the derivation a little bit tricky. It depends on G prime to the 2/5 power, and then there's a bunch of terms in there. Depends on the settling velocity to the 1/5 power. So it's got a different functional relationship that we should be able to distinguish in the lab. So he didn't really test this relationship. There was a recent paper out of Geneva in Switzerland where they tried to test this scaling relationship. Apart from the fact I don't understand the derivation, it also seems like the thickness of the boundary layer is used as a fitting parameter. So it looks like a rigorous relationship, but there's potentially some fudging factor. They're interested in it in terms of how it relates to volcanic ash clouds. The falling out of the ash is also thought to be a similar instability. So some of you who study volcanoes might also be interested in this instability. So here they've got particle concentration in grams per liter, the measured finger velocities. This is supposed to be the fit. It kind of looks reasonable, but I don't understand the derivation. It's also got this, what seems like a fudge factor of the thickness of the boundary layer. But the pictures look, pretty much similar to everyone else's. Now, the final possible relationship is that we choose something that's not from the sediment literature, but rather from the meteorology literature. So yesterday there was a lot of talks about meteorology, convection in the boundary layer, and someone mentioned Dierdorf's scaling. So Dierdorf had this, based on laboratory experiments, he looked at a flux between two fixed plates. So he's not talking about sediment flux particularly, but just a buoyancy flux. And so if you scale the buoyancy flux from the heat flux, you can measure with fancy instruments what the velocities are. And this is the relationship he gets, that the convective velocity scales like the buoyancy flux multiplied by the depth of the convective layer to the 1/3 power. So in the lab, this might be 10 centimeters. In the atmosphere, this could be a few kilometers. In the Fraser River, this could be a few 100 meters. And there's a factor of 0.6 that comes from the experimental fit. So the maximum velocities, so vertical axis is depth, horizontal axis is the convective velocities, and there's a 0.6 that comes from those relationships. So how do we compare this to the lab experiments? The assumption we might make is that the buoyancy flux is driven by the flux of the density anomaly across, so it depends upon the settling velocity and the reduced gravity. So if we plug that down here, we get another relationship, G prime to the 1/3, settling velocity to the 1/3, H to the 1/3. So we've got a few different relationships we could explore and see which one, it's not necessarily which one's correct, but which one fits the regime we're looking at in the laboratory. So these are the three relationships. They all actually have a pretty similar scaling with G prime. Eckart's is to the 1/3, David's is pretty close to the 1/3, and the new one I've made is to the 1/3, but they differ in how they depend upon the settling velocity. Oh, sorry. This is Emil. Emil's been in my lab for the last few months. Herman Klerks was kind enough to point him in my directions. He's a really hardworking, bright master student from the Netherlands, and he's been doing these experiments. And so Emil's sort of regular size, so you can see what the scale of the lab experiment is. It's small. It's about 20 centimeters by 20 centimeters. We have two layers. There's this thing we pull out, and then we get these experiments, which look very much like everyone else's experiments. Emil makes these time slices, and then we can fit the slopes from the pictures. And so he's done about 40 experiments in the lab, varying the density contrast, varying the settling velocity contrast. So, moment of excitement, what does he actually see? So the technical details, in case you care, the silicon carbide particles, but the important thing is the settling velocities just from Stokes would be really small. The fastest they would be a millimeter per second, and then the slowest ones would be basically not settling at all. So anything we see that's greater than about 0.5 centimeter per second is not Stokes settling velocity. So what do we find? We find that the particle size actually does matter. Small particles settle. The convective plumes that contain small particles settle more slowly than the particles that are large. And so all these curves I've fitted here as if you had a G prime to the 1/3 relationship. So we can fit the data quite well with G prime to the 1/3 relationships, which doesn't rule out any of the theories, but the thing that's important here is it does depend upon the particle size. And in all cases, it's much greater than the Stokes settling velocity. So how does this relate to the Fraser River? The Fraser River had really small settling loads. It was always less than 1 gram per litre, and it actually was a lot faster. And so this would be consistent if we had this relationship, so where the H became important. In the lab, it's only 20 centimeters. On the Fraser River, it's more like 100 meters. So if the settling velocity scales like the Deardorff velocity, and it depends upon the domain size, then we can reconcile this lab result with the field result. So what are the actual slopes? Emil can do some fits on a log-log plot. And what he finds is that the mean, if you're trying to fit a relationship, V to the G prime to some power, settling velocity to some power, the theory we're proposing, both those exponents should be 1/3. The average of them is very close to 1/3, 0.323. And then the exponent for the settling velocity, he finds it's 0.4. which is pretty close to 0.33 if you do a lab experiment. So I'm not going to say this theory is right, but it's at least consistent with the observations. So this is going to help inform us when we do fieldwork next May. We're going to go out on this little boat. It's little, it's about the size of one of these rows of seats, but if you've got 5 people on it, it's pretty small. We're going to go back and forth. We're going to try and measure the sediment concentration really well. measure the profiles really well and try and find out if we can scale this theory from the lab to the field situation. So I'm kind of excited by that, but the big thing I don't know about is flocculation. You know, is all this in the real world more or less important than flocculation? So I'll look forward to chatting with Carl later. Okay, that's my talk. Any questions? I'd love to take them.
Thank you, Matthew, for this talk and leaving open many questions, I guess, because we can. Okay, so. Whoop.
Okay, I come from an atmospheric science background, and what comes to mind to me are these clouds called mammatus, which have particles that are settling, and there's convection. I don't know if there's a connection, but it seems likely.
Yeah, I think Eckhart published a paper on that last year, didn't you? Saying there was some analogy between the two.
Thanks. Yes. So I definitely think there's a connection there. It's a very similar phenomenon. My question was, so very nice experiments. My question was, we discussed that there are these two regimes. One regime which is dominated by a Rayleigh-Taylor instability when you have large settling velocities, and the other one when you have small settling velocities where double diffusion becomes important.
Yeah.
Do you know your experiments in which of those two regimes they are?
I'm pretty sure it's in the Rayleigh-Taylor regime.
Okay.
So just because it's so fast. I don't think it's in this double diffusive regime. That's just my gut feeling. I haven't done a mathematical derivation to do that, but everything I went into this like thinking all about double diffusion because that's what my thesis was on when I was a youth 20 years ago. But when I actually look at it, I find it really hard to fit it into a double diffusive framework. So you know, I went into this thinking, oh, I'll explain it all in double diffusive stuff like I did 25 years ago in my PhD thesis, but I couldn't really get that to work. So I think the Rayleigh-Taylor instability is the key one, which is also what Tom's been talking about in his work as well.
Okay, thank you.
Yes. Can you hear me?
Yep.
Yeah, so very nice talk. And I'm really impressed with your way of analysis based on slope of that concentration type. And I'm wondering, that's a very powerful tool. I'm wondering, can you go back to one of the field experiments? I think it was your colleague. Yeah, so the lab part is beautiful, like a constant slope. But if you look at the field experiment, yeah, it seems to me that there's always like a two slope. I think there's another one. In one case, you actually have one slope. The other one, you actually have two slopes. Yeah, like the panel. So I think that very close to the surface, you have a milder slope. I think, is that because of this Kavli concept?
Well, it could be, I mean, there's shear, there's also some background density stratification. The other thing, it's not two-dimensional. You know, there's in the lab, we just have a long, skinny tank. In the field, you've actually got tides that move the plume north and south.
Okay.
So it's, and we're measuring at one point. So it could be the plume is being washed north or south of where we are. So that's what we're hoping to do with John Hughes Clark's experiments, because we can actually go out in a boat and chase the plume around. So, I mean, this is, the bit that's exciting about this is that however way you do it, this looks a lot faster than flocculation.
Yes,
so
that's great.
As far as I'm aware, this is the first like real solid observation of this in the field. Mm-hmm. So it's kind of exciting.
Yes.
Yep. Hi, thanks for your talk. I was a little curious about sort of upscaling from the lab to field setting.
Yep.
Especially in terms of, you know, if you have these like plume instabilities settling over like a longer depth, I would assume that the velocity would also decay with depth, sort of a la like a classical plume theory. So I was wondering if that could also be important, and if you've thought about also comparing your results to what sort of classical plume theory for a non-Brunesnesque plume would predict, and see if that could actually be useful too.
I had that same thought in the last week. I just haven't had time. I mean, I did my PhD thesis with Stuart Turner, so I really like all Stuart's, you know, he just passed away last year, but all the work he did on the Mannens-Turner-Taylor theory for buoyant plumes. So I remember it's got something about 1/3 scaling, but I just haven't had time to look it up. But yeah, that's the sensible thing to do as the next step. Yeah. I mean, there's a big crowd of meteorologists here, so you guys know this better than I would, but I'm not quite sure how you derive the Dyatlov scaling. It comes from a dimensional analysis that the velocity should increase with h to the 1/3 power, but I also remember that the plumes seem to, there's some scaling for how a single isolated plume rather than a heating plate decays with depth. But I use in field work I do on convection in lakes, I know the Dyatlov scaling also works pretty well. I just haven't looked at it. It's sort of a bit new to me. So someone who knows all about Dyatlov velocities, I'd love to talk about that at coffee break time.
Thanks. Hi. I was just wondering, so it seems like the case that you're examining is in the limit where the river's kind of dribbling out into the ocean, right?
Oh, it's not. It's actually when it's going really fast. So it's just as the tide drops, it's going at 2 meters per second, which doesn't sound like much, but you know, when we're going down with the river on the boat versus up with the river, like it's pretty whipping along.
Right. Because I'm thinking of the other situation where the river plumes are coming out with a lot of focus momentum and make these self-sharpening jets that can propagate kilometers without. So I'm wondering about, it's beyond scope of the work, but if you had anything to say about the transition from where you might have this, you know, gravitational instability here to how much inertia does a plume need to have before we flip that off and we go into jet mode?
I gather people who study estuaries know all about this. I'm not one of those, but the thing that's really missing is in the field we have a lot of shear. So we're at that instability. It's not in the lab, there's no shear whatsoever. So in the field there's very intense shear. And if you look at some of where did I have the pictures? Oh, I had the pictures somewhere. If you in the thing that really leaps out at you in the backscatters, you really see the Kelvin-Helmholtz instabilities. They're quite large, you know, like 2 meters high, and they really leap out at you. So that's the big thing that we're missing in the lab. We don't have this really strong shear. So I think that would really modulate anything we're doing. I think that's the big problem from going from the lab to the field. We're missing this fundamental issue of the shear.
I was wondering about grain sizes and grain size distribution. Do you have a feel for, did you take any samples in the field?
Oh, I did. I didn't know what to do with them. So I did the simple thing where you just put them through the filter paper and work out how much sediment's there, but I don't have a LSST to do the grain size. And I'm not set up to, like, Carl was saying, oh, you should put it through a fancy instrument in the field and see the flock size. And I think, well, I don't have that, and the boat's not very big, so I'm not.
So you didn't measure them with a laser diffractometer or even do like some sort of hydraulic
that would
settling
be a
test?
Nice thing to do, and I'd love to hear how you do that. It's just with the boats, there's not much space on the boat, so we don't really have space to do it. I'd have to take it back to the motel and do it in the bathroom or something.
Well, we ship our samples back when we're done. Yeah, we do.
Okay.
Yeah, do it at home.
Okay.
Hi, I have a question about the slide that came after Emil on the left-hand side and that noisy thing on the right-hand side.
Which one?
Emil was standing on the left-hand side and it was very noisy video on the right-hand side. It was the slide after that.
I thought I'd turn the sound off, but evidently I hadn't.
Okay. The next one?
Is that the one?
The next one, please. Yeah, this one. I just didn't remember how the slide was called. And I see Jim standing there, and I'm wondering whether we have the same question given our background on avalanches. Here you can see the first, the slope gives the speed, you say, and it's the first arrival. But if you look further into the data, you can see structure and actually waves kind of intersecting. And I'm wondering if you can say something about that, because these are, I guess, plumes that come after, if I understand.
Yeah, so it's not a front moving down. It's like all these individual fingers that's sort of moving around. So it looks like there's like two velocities. There's a sort of, this is a sort of a slower velocity, but then you can see these like other lines that are moving faster. So if I was doing this properly, I'd have a velocity distribution, but I'm not quite clear.
So the first slope is the very, very first finger, and all the other slopes are the fingers that are a little bit later.
Yeah, and they're moving within this cloud of convection. So yeah. I'm not quite sure how to think about that, but there's clearly a distribution of velocities. I'm not sure which is the relevant one. So this is probably the lowest speed that's relevant. It could be faster than this. So we're being a bit conservative about saying how fast this is. The speed we're putting on the graphs is probably a lower bound to what the speed is.
Thank you.
Do you have a question, Jim?
Yeah, great talk. What are the Reynolds numbers associated with these plumes? They're probably quite low, aren't they?
That's a good question, Jim. I don't know.
Because I was thinking, yeah, it's probably much too low for it to be behaving like a turbulent plume. And in fact, all the velocities in here look quite coherent. It doesn't look like it's all mixed up. So
they look, they look like a sort of mushroom. They're not like a classical, in training jet or anything. They're pretty gentle. Like if you play this in real time, it's really makes you want to fall asleep because they're just like floating down, going la 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 la. It's not like a jet where it's really coming out very strongly convective.
Yeah, but there's probably not that much turbulent energy in there, so it's probably not in training a lot. But yeah, like Natalie said, all those internal structures, they all seem to have the same sort of phase velocity. So
yeah, I haven't thought of calculating that, Jim. That's a good thing to...
The image processing people, they have a lot of techniques for extracting that.
They do?
Automatically, yeah.
I'd love to hear about that.
So just to follow up on what Jim and Natalie and I were saying in the context of grain size distribution, I just wonder if anyone has looked at this with respect that you have not a mono-dispersed system
so
here.
In the lab, it's pretty mono-dispersed.
Exactly, and so this is likely not mono-dispersed, right? Is that what you just said? That this is, you know what I mean? Because you don't know.
This is a lab result, and then I've done particle sizing of the lab particles, and they're pretty tight.
Okay,
I buy
and
them from
then,
a company.
so I would suggest maybe another interesting thing to do is just see what happens if you don't have a tight grain size distribution and maybe get something that is maybe a different scaling or something. I don't know if Natalie or Jim has seen anything with a wider grain size distribution.
Well, the field's I've looked at the stuff in the field. There's like little chunks of plastic in it. There's mud, there's sand. It's a real mess.
Exactly, and so that might be...
The lab's nice. The lab's this beautiful sterile stuff I buy from an industrial supplier. But the field's, that sounds challenging. I should do it though. Okay.
In the lab, I think you can do it in the lab where you have a grain size distribution that you control.
Yeah.
If you wanted to, just a suggestion.
Yeah, I think Emil's got his work. He's only here for another month before he goes back to the Netherlands, so there'll be another student next year. Yeah. Okay, thanks.
Just a quick one. I think that's a really good question. And in fact, doing this in the lab will be really useful because you can quantify the grain size distribution. But I still believe, even in the lab, because this is saltwater, you're going to have flocculation. Yeah. So then it will be even more interesting to see if the coarser grain can be trapped into the floc of the mud. I don't want to make this too complicated for you, but lab is actually the only way to quantify this. In the field, it's just too complicated.
That's a good idea.
Very good.
So I have a question. So it's a bit hard to get dynamic similarity to a phenomenon which happens on a kilometer to a phenomenon in the lab which is supposed to happen at 1 meter with the same materials. Yeah. So have people actually worried about, or have people started doing something like we do with SF6 compressed gases or some other fluids to actually mimic more dynamic similarity in these phenomena? Instead of just using the same stuff and doing the same experiment basically and getting the grain size a little smaller, a little larger. I mean, you're limited in density, right? I mean, density is a big limiter because you can't get ultra heavy materials. You can't use, uranium dust, or you can make very light stuff, of course, with plastics that works. But are there other experiments where, you're really fighting hard to get dynamic similarity in the lab?
I think I actually showed you most of the experiments have been done on this. It's not.
Pardon me?
There's maybe 6 people who've done experiments on this. So
I know. Yeah. I've been granular convection for 30 years, so people have been trying to be dynamically similar.
I think Jim's suggestion I hadn't thought about the Reynolds number before. I should check that the Reynolds.
It wasn't about the Reynolds number, about other parameters. We can talk.
Okay. Thank you very much.
Okay. Thank you, Mathew, again.